Hi, welcome. In this video, we're going to talk about Turing machines and linear bounded automata. What is a Turing machine? A Turing machine is a finite state control unit or finite state machine to which is attached a one-dimensional unbounded tape. In principle, a Turing machine is as powerful as any computer. So let's just review. We did regular languages and finite automata or DFAs and NFAs, and they had no storage. So we found out that although we could have infinite regular languages are very limited because you couldn't count things. You couldn't count the number of A's and then match the number of B's, for example. Then we moved on to push-down automata or NPDAs. We did non-deterministic, and we added a stack and context-free languages. And by doing that, we were able to have languages in which you could count the number of A's and match the number of B's and do some palindrome and some other examples of context-free languages. And it was, we added all these features by having a stack. But we also discovered that context-free languages and push-down automatas or NPDAs are also limited. So now we're going to get into the Turing machine and other types of languages. So Turing thesis maintains that any computational process, such as those carried out by present computers, can be done on a Turing machine. Now, we're not going to try that. We're not going to get so complicated with our Turing machines, but I did leave it for you to do in the discussion board. And keep in mind that the discussion board does not need to be accurate, always accurate for you to get your points, but participation counts. And that's why you get points. They're graded for participation in the discussion board. So please discuss the Turing thesis and the Church-Turing thesis in the discussion board. All right, so let's talk about the Turing machine. A Turing machine is an automaton whose temporary storage is a tape. I already said that. And the tape is divided into cells, and each cell can hold one symbol. So the tape would be like this. And on each cell of the tape, you would have, say, one symbol. There's a read-write head that can travel right or left. So you have a head that, and it's read or write. So you actually can change symbols on your tape, like to count things or to look for patterns or things like that. You can change the symbols on your tape. You can modify. And you also have a head that can start here and move here, and then come here and move back. So we will be doing examples in a few minutes. So here is the formal definition of a Turing machine. It is a 7-tuple. So it's very similar to the definition of the other automata that we've studied. We have a finite set of states. We have 2 symbols here for the alphabet. So the alphabet is a subset of the tape alphabet. The tape alphabet is everything that's on the tape, and the alphabet is all of the symbols that are on the tape, but the tape alphabet includes one extra symbol, which we use a square for that, and that is called a blank. This is the special symbol. You will notice here that the alphabet is a subset of the tape alphabet because the alphabet does not include the blank, but the tape alphabet does include the blank. The transition function, you are in a state, you process one of the symbols of the tape alphabet, you move to another state, or you stay in the same state. You either leave the symbol of the alphabet alone or change it, and then you either move right or left. Of course, we're going to do examples which will make this more clear. Q0 is your initial state, and then you have a set of final states. So here's an example of how the Turing machine works. This is the tape right here. So this is just one transition. We start here. Q0 is our initial state. We are in our initial state, and our symbol is A. So we're going to make a transition from Q0 to Q1, so I can draw that transition. So we're in Q0, we transition from Q1. Our symbol is the symbol A. right here on our tape, but we're going to change that symbol to a D, and then we're going to move to the right. So this is just a definition of what happens when you have a transition. So you could have a transition in which you stay in the same state. We'll have examples of that in a minute. This is just showing you the situation before the transition and the situation after the transition and how you can move. You can move right or left along the tape, and you can either leave the symbol alone or you can change it. In this case, we're changing it. And if you were to halt in a final state, then that means that you end up with on your tape that string is accepting. But it is also possible to not halt in the final state. It's also possible to just have something that's not defined and it halts and does not end in a final state. All right, so here is an example of a Turing machine and the different moves you can do with a Turing machine. So we have two states, Q0 and Q1. Q1 is an accepting state. So you can see over here it's defined. We have our alphabet is AB. We have our tape alphabet is A, B, and a blank. And so these are our three transitions. So you start out in Q0. The symbol is an A. If you move right, you change the A to a B. You're still in Q0 though, because we did this one right here. We're still in Q0. Now we're in Q0 and it's a B. So you're going to leave the B alone, but you're going to move right. Now we're in Q0 and it's an A. We're going to change the A to a B and move right. And now we have this special symbol called a blank. We've encountered the blank. So you're going to change from Q0 to Q1 and move left, and you're going to end up in a final or accepting state. So this string, although we changed it, but we still ended up in a final or accepting state. This is just an example of how this works. Let's run through this example again. This is an example of how the transition function works in a Turing machine. You start out in Q0. So this, I color coded it now. That's this one, it's purple. I'm in Q0 and the symbol is an A, which means I'm going to take that A, change it to a B, and then I'm going to move right along the tape and stay in Q0. So that's what I did. I stayed in Q0. I moved right along the tape, but I changed the A to a B. Now I'm in Q0 and I have a B. So that's this transition right here. I'm going to stay in Q0, but I'm going to move right and leave the B alone. So that's what I did here. Now I'm still in Q0. It's an A. I'm going to change it to a B and move to the right. And now I'm in Q0 and I've encountered this special symbol called the blank. So I'm going to move from Q0 to Q1 and I'm going to leave the blank alone, but I am going to move to an accepting state. So now I'm in an accepting state. So this is, again, just an example, simple example demonstrating how the Turing machine transition function works. So here's another example with an infinite loop. So if you can't tell here, these are the arrows that go this way. So I'm in Q0 with an A. I'm going to leave the A alone and go right. Now I'm in Q1. There's a B. I'm going to leave the B alone and go left. Now I'm in Q0. There's an A. I'm going to leave the A alone and go right. Also move to a different state. And now I'm in Q1. I'm going to leave Q1 alone. I'm going to leave the B alone and go left. And here's another demonstration of the same thing, only color coded and animated a little better. All right, so I start out in Q0 and it's an A. Now I move to Q1, it's a B. Now I go back to Q0, it's an A. Now I go back to Q1, it's a B. So this is just an infinite loop that's just going to keep going back and forth and back and forth. It's never going to end up in any accepting state. It's never going to find the blank. It's never going to get there. It's just going to keep going back and forth. And again, this doesn't demonstrate any particular language. It's just demonstrating what an infinite loop on a Turing machine looks like. So let's go over what the standard Turing machine is. It has a tape that is unbounded in both directions, allowing any number of moves to the left or the right. It is deterministic in the sense that the transition function defines at most one move for each configuration, but not all moves are defined for all configurations. So we don't have multiple moves for on a transition, but you don't, like a DFA where you had to define every single move for every transition, you don't have to do that. There's no special input file. We assume that the initial time the tape has some specified content, and some of this content may be considered input. There's no special output. Whenever the machine halts, some or all of the contents of the tape may be needed for the output. And any configuration is completely determined by the current state of the control unit and the contents of the tape and the position of the read-write head. All right, so let's try an actual example. This is a regular language. So this has an error on it. You can see I have over here Q21. So this should be Q1. And this final state should also be Q1. I'm going to have to fix this on the slides, or maybe I'll wait and see if anyone points it out. So we have our two states, Q0 and Q1. We have our alphabet, which is 0, 1. We have our tape alphabet, which is 0, 1, and the blank. And we have our final state, or accepting state, which is Q1. We have two transitions. So if you are in Q0 and you get a 0, you stay in Q0 and you move right along the tape. If you are at Q0 and you encounter a blank, you move to Q1 and you move left back on the tape. So here's an example. We have this. This is our tape. So here we start Q0. So we are in Q0 and we have a 0. So we're going to leave the 0 alone and we're going to move right, and we're going to stay in Q0. Now we're in Q0 and it's a 0. We're going to leave the tape alone and we're going to move right. So now we're in Q0. We're in Q0 and it's a 0. We're going to stay in Q0 and move to the right. So now we are in Q0. This transition right here. We encountered the blank. So what are we going to do? We're going to take the transition over to Q1, leave the blank alone, but we will now go to Q1 and move left, and then we are able to end up in a final or accepting state. So this string is accepting in the language. Here's another string. We'll see if just one single 0 is accepting. Q0, 0, you move right. Q0. Okay, we have a blank. So we go to Q1 and we move left. And this is also accepting in the language. What about this string? Well, we are in Q0 and we have a 1. There's no transition defined for Q0 with a 1. We haven't defined any transition for that. So we are not going to move anywhere. We're not going to do anything. We're never going to get out of Q0. We didn't define a trap state, but we could have defined a trap state. But we didn't really need to, because if you're never going to get to an accepting state, then that language is not going to be accepting. Also with this one, we're never going to get to an accepting state with this string right here. Or with the string 0, 1, 1, we would start here in Q0, we would move here, and we would also again, gets stuck right there. So any string that is not accepting, even though it's not defined, we're never going to get to the accepting state. But this string right here, you can go through it. You just keep moving right and moving right and moving right and moving right until you hit the blank, at which point you go to Q1 and move back. So yes, this is an accepting string in the language. All right, so in the next video, we're going to do more complicated examples of Turing machines with some more complicated languages.